In this video, we're going to take a look at some improper integrals and strictly determine if they're convergent or divergent. So you can imagine that each of these integrals, maybe we aren't able to solve it for whatever reason, but it still could potentially be valuable to at least state if it's convergent or not, even though we can't solve for what it converges to. And we're going to use the comparison theorem to do this. All right, so with the comparison theorem, here's the comparison theorem. The idea is we want to get a function that's either greater than or equal to this function, to the integrand, for the entire domain, or at least for the entire limit of integration range, or less than or equal to the integrand. And which one, it just depends. You would have to just play with it. So I worked out these problems on my own before this video, so I already know what we need to do. But in a real situation, you'd probably have to play with it a little bit, because what we're going to do is if we find a function that's greater than or equal to this function, this integrand function over this range, and that function that we found is convergent, then we know that this must be convergent. But if we find that that function is not convergent, then we need to come up with another function that's less than or equal to this function and check to see if that's convergent. And so you don't really know what road to go down first. You just have to play with it. Now, one thing to note is that, so you might get a problem where, let's say the integral or the integrand is not defined at like 0 or something like that. Well, you can then just do the comparison theorem for going from 1 to infinity. And then if you find that it's convergent, let's say, well, then as long as you can verify that going from 0 to 1, let's say, it's just like a continuous function, but then the whole thing must be convergent, right? So you're not totally constrained like to this exact range here based on the limits of integration. We could do this problem going from 1 to infinity. And if we found that this was convergent, then wouldn't you agree that going from 0 to infinity, it's also convergent? Because if you plug in 0, you get, this is continuous everywhere from 0 to 1. You see? Okay. And actually, we're going to do that here. So we know that x, the integrand, this is always less than x over x cubed, if we just remove the 1, right? Because for all x, as long as we're greater than 0, this is always true. Because for all x greater than 0, you're always, the numerators are going to be the same, and the denominators on this side is going to be 1 unit higher than this side. Okay, so this is x over x cubed is 1 over x squared. Okay, but we're going to do the comparison theorem going from 1 to infinity, because we can't do this going from 0 to infinity. What we could do like an improper integral in that case, it would be a type 2 and type 1 improper integral, right? We'd be taking like the limit as t goes to 0 from the right, but we don't want to make this problem more confusing than it needs to be. So why don't we just do this? Why don't we say, is this convergent? Okay, so this is equal to the limit as t approaches infinity Okay, so this is equal to the limit as t approaches infinity of minus 1 over x. We could let's take out that minus. So 1 over x from 1 to t. So 1 over t minus 1. And we can let's bring the minus back in. Okay, so as t approaches infinity, this goes to 0, so this limit goes to 1. So this limit, this improper integral is equal to 1. And so since 1 over x squared is always greater than this function for going from 1 to infinity, and 1 over x squared is greater than this function and it's convergent, 1 over x squared going from 1 to infinity, that means this must be convergent according to the comparison theorem, and that makes perfect sense. Think about it. This is convergent. But this function is always, for going from 1 to infinity, it's always greater than this function. So from 1 to infinity, this is convergent. But this is going from 0 to infinity. Is that an issue? So how do we interpret that? Well, okay, let's say that this, like, yes, this, if we were going from 0 to infinity, we'd have to treat it as a type 2 and type 1 improper integral. And we have to determine if it's convergent. You know, maybe it's not convergent when you approach 0, right? That's an infinite discontinuity. But this here, at 0, what is this function equal to when x is equal to 0? 0 over 1 is just 0. And then going from 0 to 1, it's just continuous. There's no like infinity aspect to deal with. This is just going to be going from 0 to 1. This is just going to be some continuous curve with a finite area. So if we know going from 1 to infinity that this is convergent, then just going from 0 to infinity, then it's definitely convergent. This, going from 0 to 1, this is for sure convergent. So that's the proof that this is convergent. Now, if, again, just to make this clear, if there was like an infinite discontinuity at x is equal to 0 for this, not this, for this, then we couldn't say, we'd have to do further analysis. We couldn't say that this was necessarily convergent, even though it's convergent going from 1 to infinity. But since it's continuous from 0 to 1, then we can. All right, here we're going to say that, so let's drop the x here. If we drop the x, then going from 1 to infinity, this is always greater because you'll always have a smaller denominator. The numerators will be the same, but the denominators will always be smaller. Well, this is x to the 4th, right? Everything's the same except we've dropped the x. So for all x from 1 to infinity, this will always, everything's exactly the same except this minus x, so this will always have a smaller denominator, so this is always greater. All right, and so the square root of x to the 4th is x squared. Okay, so let's see if this converges or diverges going from 1 to infinity. So 1 to t Okay, so let's evaluate the integral. We've got 1 over x dx plus, so natural log of the absolute value of x evaluated from 1 to t plus, okay, the integral of 1 over x squared is minus 1 over x. So we've got natural log of the absolute value of t minus, so okay, so this is equal to the limit as t approaches infinity. So infinity is always positive, so we could just take away the absolute value. Okay, so this, as t goes to infinity, this goes to 0. So all this goes to 1, but then this goes to infinity, so this is equal to infinity. Now, since this is always less than this, over from 1 to infinity, and then this diverges, that means that this must diverge. So this is going to diverge. Okay, here, so x to the first times x to the 1/2 is x to the 3/2. So we want to say that if we use x to the 3/2, 1 over x to the 3/2, and then going from 0 to 1, secant x is always positive. It's never like it's never equal to 0 at 0 or 1 or anywhere in between. And so since this is always a positive number, then the integrand is always greater than this from 0 to 1. Okay, but in this scenario, this is an improper integral of type 2. Type 2 improper integral. We're not going to infinity, but at 0, we have an infinite discontinuity. So we're trying to determine let's imagine we can't evaluate this integral, but we still want to determine if it's convergent, if going from 0 to 1, including this infinite discontinuity. So what we're going to do is we're going to say the limit as t approaches 0 from the right of x, so minus 3/2 dx. So this integral minus 3/2 plus 1 is minus 1/2. X to the minus 1/2 over minus 1/2. Okay, so we've got minus 2 minus 2. So this is 2 over root t minus 2. Okay, so we can take out a 2. Okay, so approaching 0 from the right, 1 over root t goes to infinity. Infinity minus 1 is infinity. 2 times infinity is infinity. So this diverges, but this is always less than this. That means this must diverge as well, according to the comparison theorem.